When most people think of cooling computers, they think of those fans that spin up when the motherboard gets hot. In data centers, they often use water for cooling, but a new trend uses solid state cooling. Learn all about it on this episode of Future Proof.
The future is here already. It's just not evenly distributed. Yet. Today's world teems with innovation. The nexus of hardware, software, and human ingenuity promises a revolution in possibilities. What does tomorrow look like? Witness Future Proof.
Yours truly, Eric Kavanagh here. And folks, we're going to talk about something that's very cool today. We're going to talk about data centers. Obviously, that's the hottest topic in the world of AI infrastructure. Data centers are cropping up left and right, but there's a lot of electricity that goes into them, a lot of power consumption, a lot of heating happens because of these servers humming away all night long as they're training AI models and getting the job done. So how are you going to keep it all cool? And our expert today can tell us all about that. So I'm very pleased to have Larry Yang with us today. He is with Phononic. They're based in North Carolina, I believe, but they got offices out in San Francisco and all over the place. And you folks are doing some really interesting work in the bread and butter, really important category of keeping things cool, right? Tell us about the latest.
Yeah, that's right. Thanks for having me on, Eric. Yeah, Phononic's been around for over 10 years now, and we started with cooling optical transceivers within data centers. Optical transceivers have little lasers in them. They're the ones that sit on the ends of the fiber optic cables. They send the data across to wherever the data needs to go. This very show is probably being transmitted over fiber optic cable somewhere, and it's probably using our product.
Right. Ah, that's pretty cool.
As
And
data
then
rates, go ahead. Sorry.
yeah, and then you've got all sorts of other products, but let's maybe focus on the kernel where this all started. I'm fascinated by the material science and by the hardware innovation around this, and like how I'm curious how long is that cycle? Like, because we're seeing these cycles condense. It used to be with chips, it was 10 years from ideation to manufacturing. Now it's like 2 to 3 years in certain use cases. And that's pretty exciting stuff because then you can address market demands much more rapidly and stay in tune with what the market needs. So tell us a bit about how we got here for your first product and the material science and all that fun stuff.
Yeah, absolutely. So the core technology that we run on is what's known as the thermoelectric principle. It's also named after a French physicist, Peltier. So sometimes it's called the Peltier effect. And the concept is relatively straightforward. There are certain materials that have a property where when you apply an electric current, one side gets hot and the other side gets cold. And you can reverse that current and the other side gets hot and the other side gets cold.
Hmm.
Build solid state refrigeration. You could also build heaters out of it as well. And in fact, we take advantage of some of that. So what we do is we take a wafer of this thermoelectric material. It's bismuth telluride is the particular one we use. There are other materials that have this effect. And we singulate them or cut them into little what we call legs. We sandwich those legs between two ceramic substrates, and we have a thermoelectric chip, thermoelectric module. We
Hmm.
can make a variety of different sizes. We can make ones that are as small as a grain of rice. The lasers I mentioned in the optical transceivers will sit on top of those and stay cool. We can even make ones that are as large as a half dollar, and we can actually put multiple ones onto a single board to deliver higher capacity for cooling. That's what we use in our products in commercial air conditioning and heating. So everything
That's
from a grain of rice all the way up to a 12 by 12 inch module, all possible.
This is fascinating. And these are chips. So, when people think of cooling, they think of fans blowing, for example. That's the old-fashioned way. But you've actually manufactured a chip that takes electrical current, and if it goes one direction, it cools one side, and you can flip that if need be. It's in the other direction, and it cools the other side. Is that right?
That's right. And it's more than just the chips. I mentioned how we can put multiple chips together. So we actually have control electronics and software that can operate them and turn them on and off at different times to keep it efficient. We also have the heat exchangers that could be an air-cooled sort of heat sink, if you imagine, with fins and all that, kind of like in a radiator of a car, or it could be a liquid one, a lot more like a radiator in a car. So we can integrate our chips into those sorts of systems, and we actually provide all of those services to our customers. So we are providing very turnkey design services so our customers can quickly get to market with whatever shape or size their thermal problem is.
Hmm. That's fascinating. I remember watching as the solid state universe really transformed compute, and you're seeing that today, like with NVMe, one of my clients, a very cool company called Hammerspace. Their previous company, David Flynn's previous company, focused on that NVMe protocol and designing it for these amazing devices. And now you can get crazy speeds on data ingest. There's another company called Ocient. They're doing hyperscale data warehousing because they built this architecture where they can leverage arrays of these NVMe friendly solid state drives. And so what's interesting to me is that so much changes here, and a lot of the folks back in the engineering room have been figuring out how to optimize the flow of electricity through these environments, through these computers, these supercomputers, these GPU servers, for example. And now here you folks come along and you're doing the same kind of thing, but on the cooling side. So it's really this fascinating new direction that really does spin out of an awareness of material science and what these different types of materials can do, right?
Absolutely right. If you look at the history of electronics for 50, 100 years, or 100 years, there have been a trend from moving from some sort of mechanical analog or functionality to a solid state one. You listed a bunch of them. Computing was that way, disk drives and storage is that way. And we're doing that now with cooling. Solid state means a couple of things. One is no moving parts, so nothing to break down. It also means that it is much faster response. There's no liquid pump that has to turn on and off.
Hmm.
It's also smaller. So one of our opportunities is when you look at how a data center is being cooled, 40% of the energy that goes into a data center is spent on cooling. And that's
Hmm.
because cooling is so slow to respond, they will set the cooling for the worst case and just kind of set it and forget it and let it run. So a
Right.
lot of the time it's being overcooled because your traditional cooling system just cannot be very responsive. With solid state, you become a lot more responsive. So we can turn on and off the cooling right when you need it. So we can be a lot more efficient and save a lot of energy and improve the performance efficiency.
Yeah, that's fascinating. And I'm guessing a lot of this spun out of research. Is that kind of where the genesis of this whole concept came from, like a university's research or something? Or how did this all begin?
Yeah, that's right. When we started over 10 years ago, as I mentioned, we were a lab based inside North Carolina State University. So we definitely took advantage of space there. Some of our early employees were researchers there. And so that is how we got our start.
Hmm. That's fascinating. And then you kind of see the product roadmap. What does it take you now as you look at the market opportunities? How long does it take you to go from ideation to first prototype to manufacturing and distribution?
Yeah, there are a couple of different ways to think about it. So one, as I mentioned earlier, is how we offer very customized solutions. So an optical transceiver company or some data center cooling company customer would come to us with their particular problem. And within a week, it could be as quick as a week, our engineers would build up a thermal model of not just our chips, but of their entire subsystem and
Wow.
can analyze where the hotspots are. And then we'll actually design a customized thermoelectric chip for that application. And in about 8 weeks, we can fabricate a prototype of that, ship them a dozen parts. They can put it into their system and do some prototyping or measurements, ensure it does the right thing, and then we can go to mass production right after that.
That's
We can be
crazy.
pretty quick because we are customized. We're set up to do these sort of customized types of solutions with all of the services required to deliver that. So that's one part of the other. And the other is as we go into these more substantial opportunities, what we'll do is we'll again work closely with customers. Maybe it's a GPU vendor, maybe it's some other part of the data center, a network switch, an optical integration type of a problem, where it may require a more extensive type of a system design. But again, our engineers will engage with them and there may be a little bit more prototyping, could be kind of a couple months, build a proof of concept, build a prototype. They may have to pitch it to their customer. But that has to then align to the innovation cycle of their customers. And so that could be anywhere between 3 months to 18 months, again, completely depending on the problem that their customer is solving.
That's interesting. I'm also remembering, because I've been around for a while now in this industry. I remember the era of converged infrastructure, and one of the cool observations I've heard on this show many years ago, we were talking about appliances and how you see appliances come around when the limits of software at that stage in development are reached. And so you come up with an appliance and you get that hardware software mix blend really to kind of change the dynamics and go forward. And then this whole converged infrastructure thing happened. Is that was that part of the sort of zeitgeist, if you will, out of which this concept came? Because it's really quite fascinating to think about how partners are now working together so closely to create these products. Because you get down to cooling, it's so important. You have got to cool these boxes, or they're going to burn and blow up. That's not good for anyone, right? When these things fail. So we've been on this really interesting arc of innovation the last 15, 20 years, and it seems like you guys are really riding that wave. Is that about right?
Yeah, if you look back at my career, I've always looked at how we can integrate hardware, software, network, and systems, and be able to move up and down that entire software and hardware stack to solve a particular problem. I've
Mm-hmm.
been doing that here. Did it at Fitbit, at Google, Microsoft, Cisco, Sun Microsystems way back in the day. It was always sort of that type of an integration, and it's the same thing here. We don't just sell you the chip. A lot of our competitors will just sell you a chip and say, good luck, read the spec, and
Hmm.
hope you buy a lot of our parts. We take a very different approach. We are with them in the design phase. Like I said, we help them simulate the actual thermal problem and their system problem so that we can be partners with them. We may tell them, hey, why don't you change your packaging a certain way, or move your heatsink a different way, move a connector a different way. So it's a real integrated type of conversation. Our solution requires some software algorithms as well. So we'll work with them to integrate our software into their software. And so this way, kind of like you said, it's a very integrated type of approach. And so we can make the trade-offs at whatever level is appropriate to be able to optimize the design. And modern design tools today are really support that. They're very standard types of simulation tools. There's of course, Zoom calls and other things, file sharing. It makes it, a lot of today's design tools just make it very easy to move quickly in such an integrated way.
That's really cool. And in that design phase, I mean, you're basically creating a digital twin of the device, right? You're getting information from your prospect or your client about the materials that they're using, what's the voltage, all the details about how it's going to operate. And then I'm guessing you go into one of these design environments and you are essentially creating a simulation of that environment and testing it and running it. And as soon as you feel pretty good about where it's going, if you're on the right track, that's when you pull the trigger and pull out the prototype process, right?
That's exactly right. Our engineers use tools like IcePack, Modelica, ANSYS. These are all computational fluid dynamics type of simulations. It could be done at a very simple level or a very deep 3D modeling level. All of our customers use those same tools. We'll build a model and share it with them. They could plug it into their bigger model, or they may give us their bigger model and we'll plug in our piece. And I think digital twin is a very good way of describing it. Everything is done in the digital world. We simulate it all and get it all right before we commit to start building actual hardware.
And here's kind of a hard, maybe curveball question for you, because I'm really fascinated by digital twins. I've been covering them on and off for about a decade now.
Mhm.
SAP did a bunch of work in that space a number of years ago. The client I mentioned a minute ago, I think Hammer Space, they're very good for digital twins in some of these environments. What I think is really interesting is taking data from the real world and patching that back into the simulated environment. So you learn things about this material or this chip design or that chip design. How does that get baked back into your simulation environment? In other words, how does the data that you gather and how dynamic is that versus how manual do you have to be to leverage the learnings on working in this project and that project over time to kind of build out your compendium of data of fact tables, if you will?
Yeah, I can cover that in sort of two different ways. One is I can talk about our IoT platform that we launched for connecting some of our devices, and then the other I could just talk about how we iterate and learn on our core technology. So one of our products is a cold chain fulfillment solution where we sell refrigerator and freezer totes to online grocery operators to improve the efficiency of their online grocery operations. Every single one of these totes is connected to an online cloud. They're all IoT enabled. They have Wi-Fi. They send data up. And we have a dashboard, an API, and a database that our customers can use to ensure that that your order is maintained at proper temperature. So if there's like an excursion from temperature, an operator can go make sure and figure out what's going on. They can monitor their energy utilization so that they're not leaving empty totes on power, and other sorts of capabilities like that. So IoT, as I'm sure you're aware, is pretty core to the whole concept of digital twins. So you can do exactly what you're just saying, get data from the real world and feed them
Right.
right back. And so we've done some of that. We were helping a customer put our totes into an installation that was somewhat constrained from an airflow standpoint. And so some of the totes were getting overheated. And so they would actually put the totes into their structure, and then we would look at the temperature data and the airflow coming real time out of that on our
Oh,
dashboard, and then
right.
feed back to them and say, okay, it looks like you have a hot spot in the upper left or a little more airflow in the lower right, and quickly digitally iterate on what they were seeing in the real world in their enclosure, give them feedback and help them optimize their design. One of the great things about solid state is that it is very fast response. And so when your target temperature is deviates a little bit, we can quickly turn on and off in order to
Interesting.
maintain that. If you compare that with a traditional vapor compressor, a vapor compressor is a motor and a pump, and they turn on and off, but it's a much slower response. And so if you were to put a temperature probe into your typical refrigerator, you would see anywhere between a 2 to 5 degree variance in temperature. And so if you're maintaining something like you were saying, vaccines, cord blood, and those types of things, that type of variance could be very detrimental. So
Hmm.
we've actually built medical refrigerators that have the maintain temperature variation within half a degree, so that you can keep that tight tolerance for the very sensitive materials. And again, it uses our solid state materials so that we avoid the need for those mechanical vapor compressors. So there's no
Yeah.
moving parts of solid state. There's another big advantage, which is in those with those vapor compressors, they use hydrofluorocarbon refrigerants. Hydrofluorocarbon refrigerants are 2,000 times more harmful on the environment than CO2.
Wow.
So we can
Wow.
actually eliminate a greenhouse gas warming chemical from being used.
Well, and I'm also thinking to myself, just for user friendliness, those motors make a lot of noise, right? Like
Right.
we just dealt with power outages all through this area because of a storm, and some people have generators, and that's great when you got a generator, but it's loud. It makes a lot of noise. It has a lot of exhaust, obviously, and that's one nice thing about solid state is that it doesn't make any noise, right?
We actually had a customer who put our medical refrigerators into a neonatal intensive care unit, and the nurses there noticed how much quieter the refrigerators were, and they noticed how much better the babies slept because of
Wow.
it. And so they
That's
actually gave
funny.
us a little testimonial on that. So you're absolutely right. The noise is a problem with traditional refrigeration.
Yeah, that's pretty funny. And I'm thinking, was talking with the wife and friends last night about these power walls. So
Mm.
Tesla, I'm sure has these power walls. One of the challenges with solar energy, and I think we just saw this play out over in Spain. One of the theories I've heard is that the reason they think that maybe that whole grid crashed was because they had gone all renewable for a day, and then they were trying to go back to some sort of a balance, and apparently there was too much solar power coming in, and it disrupted the grid. Well, these grids are insanely complex. I mean, the manner in which you manage these things today is really, I mean, state of the art technology and knowledge and awareness. But where I'm kind of driving with this is that the better you can understand and control the flow of energy in your business, in your devices, whatever, the better off you're going to be. What do you think about these power walls and how big a deal is that? And are you in that space? Are you possibly going to be working on cooling those kinds of things too?
So I love Powerwalls. I actually have one, and it has kept the lights on literally
Nice.
in our house. Um, I think the whole battery storage is critical to where we're going in the industry overall, especially with the less predictable energy sources that you were just talking about. Um, Batteries do get warm. We have actually talked to some automobile vendors actually about how to keep the batteries on in the vehicles at the right temperature, because as you know, the performance of a battery and the charging time of battery um, definitely is impacted by the operating temperature. So we've actually talked with folks in the electric vehicle space about helping them with that problem.
Yeah, that's cool. So what are obviously you've got all sorts of medical equipment where you're coming in handy, servers, computer equipment, things of that nature. What's the balance? Are there significant challenges in one environment over the other? Maybe let's talk about medical devices. You talked about the one of your first ones. Is how big a market is that for Phononic? Like how many different kinds of devices are you in, and what does that whole process look like?
Yeah, interestingly, the biggest challenge is, less the technical piece, but I'll call it the business piece. There are so many things that could use our technology to cool that we can't possibly go and build every single one of them.
Right.
And so at times find ourselves turning away engagements because we just don't have time.
Hmm.
And so we realized this a couple of years ago, and so we've moved to a business model where we emphasize licensing. So our engineers will build a reference design, sort of a starting point for a particular application, and then we will then have companies license the technology, and then they'll make the modifications required to suit their particular application. I'll
Hmm.
use that e-commerce grocery tote as an example. We have a number of installations. Sam's Club has an installation. ShopRite in the Northeast, you may be familiar with those guys where you're at. They have an installation, but we have another set of customers who will come and say, "I love it, but can you just make it a little bit taller, a little bit wider? Can you make the lid open this way? I have a robot that has to handle it. Can you move the gripper things?" And we can't say yes to every single one of these. So we've had some customers who then license the tote design, and then we'll introduce them to our supply chain, who manufactures them, other experts who can help them with modifications, and we'll say, "You go ahead and do whatever you want with the tote. We'll help you, but you take it the rest of the way." And in addition to just the development part, those people understand their markets even better. So, like the medical refrigeration one is a very difficult market to sell into because it's very regulated, and there are a lot of approval cycles you got to go through. And for a startup to have to really invest in all of that is very challenging. And so, we would much rather license the design to a company who's already in that space, who already understands those customers and the regulations and all the use cases. They can then take our product, make the modifications, and then sell into that. So we actually did that in a few years ago, a company called Thermo Fisher. So initially, we started making the under-counter vaccine refrigerators ourselves and tried selling them, and then we
Wow.
realized what a hassle that was. So we engaged with Thermo Fisher. They actually then picked it up, put their brand on the product, and sold it through their channels, and we were much more successful working in that model.
That's cool. That's really cool. And I'd like to get back into the data
Okay.
side of things too. I'm guessing you've got some kind of a data science environment that's probably akin to the high performance computing world, which of course is very much focused on life sciences and very, very dense challenges from a both data perspective, but also from a maths perspective, kind of understanding how to run the numbers and figure out what would the proper design would be and like how much material to use. All these things are very, very, very specific and data intensive. So do you have a sort of data science program? And if so, can you tell me a bit about that?
Yeah, we material science is definitely at our core, and we have models for different types of materials, material properties. But in addition to that, I talked about how we take these wafers and singulate them into these legs, and then we sandwich them between the ceramic substrates.
Hmm.
That's an oversimplification of what we actually do. You can imagine taking a bismuth telluride leg and trying to solder it between two active ceramic substrates is not
Yeah,
an easy task. So
yeah,
there are actually other materials we have to introduce, aluminum nitride or tungsten and other things. It's literally a solder type of process. So there's temperature variations and temperature profiles. And so we have spent a lot of time, I'll say, tinkering with the chemistry. Every time you add some of that other material, you're reducing the amount of total available bismuth telluride. And so you're actually reducing the effectiveness of your thermal heat pumping. And
right.
so a lot of our intellectual property and patents are around minimizing that overhead so that you maximize the amount of bismuth telluride you have available. And ultimately, that's what results in the higher performance of our
Hmm.
thermoelectric electric chips. So a
That's
lot of science. It's certainly not something I'm equipped to go in a lot of detail in. The engineers and our material scientists can talk a lot more about it than I possibly could.
yeah.
But that might give you the flavor for that world of data, if you will. We model all of that. We have all the physical properties, and our engineers go in and make all the trade-offs. They'll build some experiments to do a whole design of experiments type of thing. Okay, let's vary this dimension this way. Let's vary the temperature this way. Try to figure out where the sweet spot is to build some stuff. Okay, that
Yeah.
didn't work. Sweet spot's here. Now let's do another set of experiments, etc.
Yeah, a lot of R&D for sure. And the data center push is just white hot, no pun intended here. You see, of course, the hyperscalers buying up just tons of space, GPUs, et cetera. NVIDIA is still off the charts. And there is all this talk about rare earths and rare minerals and the things that you're talking about, being able to get access to these things because there are places where there is a fair amount of it and there are places where there's not much of it at all. From the sourcing perspective, how much of your manufacturing takes place in stateside in the United States? How much of your sources? Do you have a pretty sprawling supply chain? How does that work?
Fortunately, we have a relatively simple supply chain. We do have manufacturing in the U.S. and we also have manufacturing in Thailand. We do source our materials throughout Asia. Um, and bismuth telluride is not a material that's difficult to find. It's an easy material to find. So fortunately, we're not as constrained by that. They're like I'm trying to remember they're both byproducts from some other type of an operation. So fortunately, we don't that's not as big of an issue for us. So, but you're absolutely right around the data center growth. The amount of power and cooling that they're talking about there is incredible. A lot of people just talk about the electrical requirements that these data centers have, but it's important to keep in mind that every watt of electricity that goes into a data center turns into a watt of heat that ultimately has to get out of the data center. And so
Hmm.
when we talk about that 5 gigawatt data center that they're building down in Texas, that's 5 gigawatts of heat that thing is giving out, which is enough heat to heat up a city twice the size of Detroit throughout the Michigan winter. So it's a phenomenal amount of heat that has to be managed there.